Okay.
Physics sucks.
Hey, if you're doing a screencast right now, can I go outside and study because
Oh my god, Ben.
it'll be better for everyone.
So we're going to look at the fundamental theorem of calculus. We're going to look at it in two parts. Part one is basically when you take the derivative of the antiderivative, you get back what you started.
Makes sense.
Okay? Make sense? Right here. The derivative of the antiderivative, you get back what you started. So derivative of the antiderivative, equals original. Okay, so I'm giving you y. Y is defined as an integral. So when I do dy dx, basically, do you see how in the integrand it's with respect to t and then it says dt?
Yeah.
And then you see in our bounds, the x, no, actually, you don't have to do anything. Basically, you get back 1 over 1 plus x squared. You see right here, it says f of t. It's kind of like just replacing the upper bound with that variable. So your integrand is going to be defined as some other variable. In this case, it's t. So when we do the derivative with respect to x, we're going to replace that x with the t.
Okay. Why?
Good.
No.
Why? So imagine, okay, so remember when we did antiderivatives?
I'm
Right.
gonna be honest, I'm not exactly sure what an antiderivative is.
Let me just
I do know what an antiderivative
okay, so usually when we define an antiderivative, we use the capital letter F. So let's say I end up with capital F, guys, and we evaluate that from 0 to x. Following so far? So what does that mean? That means we're going to plug in, so it'd be capital letter F of x minus capital letter F of 0.
Yeah.
Okay. This is the antiderivative. This is what we did in the last class. Now, imagine if we took the derivative of this. What would that be? What's the derivative of capital F of x? It's lowercase f of x.
Oh yeah.
And what happens when what's this? Well, this is just a constant. So what happens when we do the derivative of a constant? It's just going to go away. So when we take we take something like this and we do the derivative, we get back the original function, but evaluated at that upper bound.
So
No.
we should really be changing the t to an x, not the x to a t.
The t to an x, right. Now, the lower bound, it has the letter a. So I put in here a 0 for an example. It doesn't matter what the lower bound is, as long as it's a constant. Because when we do the derivative, it's always just going to go away. Exactly. So that's basically all the work you have to do for this one. Here, what's dy dx? So I just check my lower bound is negative pi, which is a constant. So it's just going to be cosine of x. Again, if you want to just think of it as replacing the variable with that upper bound.
Okay.
Now that's in the basic form. So what are we really doing here? We're doing dy dx, which is a derivative. So there are occasions where we have to apply the chain rule. It's not, oh goodness.
I don't get being drunk. My house just puts this
As I could prove this the long way. What I'm basically showing you is the fundamental theorem of calculus. This is how it will apply. Just here, let's say I have negative pi to x. What's the antiderivative for cosine?
Cosine.
It's sine of sine of t, evaluated from negative pi. So what happens here? I get sine of x minus sine of negative pi. Now, this is what y is equal to. So now tell me, what would be dy dx? What's the derivative? It would be cosine of x.
Cosine of x minus the negative three.
What's the derivative of this? 0.
So it's whatever in the
So messed
side.
up.
I'm basically showing you that
No,
you
yeah.
don't have to actually find, when you do the derivative of an antiderivative, there's no work.
Got it.
There's no work to do. Because you'll always
Okay.
end up back with your integrand
Okay.
evaluated at the upper bound. The lower bound will always go away. It will always end up being 0.
But that's just if it's just x.
Got it. So now we're going to continue with the next example. What happens when we have an x squared? Okay, so the first part is going to look, so the first part's going to be cosine of x squared, but then we're going to multiply everything by the derivative of the exponent. Because if we were to apply that same concept, you know, where if we were to write it all out, when we would go to do the derivative of sine of x squared, we would get cosine of x squared times 2x. And then I'll just rearrange it, so
Why do you need to multiply by 2x?
chain rule.
You multiply it by the
But why do you have to use a chain rule? Why can't it just be?
Do you want me to prove it again?
Oh, yeah.
Do you get it?
No, yeah.
Because see, like, imagine here, imagine if this was an x squared,
You
and
have
then
to
I did the
change- you have to do-
derivative.
Okay, got it.
Okay, next one. What's the next one look like? So dy,
Don't say anything.
I won't say anything.
Oh, yes.
So we're going to take negative 2x. The fact that it changed into a u and du, that's kind of irrelevant. You're just going to plug in the negative 2x where u is. So it's going to be,
Could we do, like when we're doing our homework, change it to the y first, like the regular equation, and then
if you want, it's just, sometimes that won't be possible. So you need to know the fundamental theorem of calculus.
why do you not multiply that all by
Oh.
negative 2?
Thank you. I forgot.
Oh.
Question. Why doesn't the 5 go away?
So it should be 16x to the third plus 10. Is that better?
Why didn't that 5 go away?
Okay, so remember, if we were to do the if we were actually to solve this, it would be u to the fourth over 4 minus 5u.
Yeah.
So when I do the derivative, the 5 is still there, right?
I hate this.
Remember,
Can we do like,
it's the derivative of the antiderivative. So we're left with the integrand.
Oh. So you already have the derivative, so it's not.
Exactly. Okay, now, sometimes our lower limit is not a constant, or in this case, they're switched. So our rule only applies when the variable is in the upper limit. So there was a rule that we applied on the last quiz. Right, if we change it to a negative, that allows us to switch the bounds. So dy dx is going to be negative 3x sine x, and in this case we don't have to apply the chain rule, so that's our answer. Okay, the next one, we have a situation where we have lower and upper bounds. Both have a variable. So what we're going to do is we're going to separate this using the additive property. So I'm going to separate this into 2x to 0 of 2 plus e to the t dt plus, and then go from 0 to x squared of 2 plus e to the t dt. Now the fact that I use 0 to break this up, the 0 is kind of irrelevant. We can use any constant that we want. We can use -2, we could use pi, we could use 1,000. just pick any constant. That constant doesn't necessarily have to be in between 2x and x squared. We just need to be able to break it up into two separate parts. Now, what do I need to do with the first one? I need to get the 2x to the top. So I'm going to make the first one a negative. I still haven't done any derivatives yet, so just switch this to a negative, switch the 0 and the 2x. And the second one, is the second one okay? What's the question? It does look like a plus. Now we'll do dy dx. Okay, so the first one, we're going to plug the 2x in for t, but then we have to multiply by 2 for the chain rule. So it's going to look like this. It's going to be negative 2 plus e to the 2x times 2. Let me pause there. Any questions?
You have to do times 2 because it's 2 hours, right?
Right, because it's you always end up multiplying by whatever the derivative of the top is. Questions?
Where's the negative from again?
The negative because we switched the 0 and the 2x.
Oh, right.
Okay, now what? What's the next part look like?
2 plus e to the
E to the x squared times 2x.
2 times that.
Uh-huh. And you could factor. I honestly would just leave it. There are places where I'd want you to simplify, but for this one, I don't bother. Any questions on that? That's as hard as those types of problems get, by the way. Like where you have a lower and upper limit that you have to separate and switch and then apply chain rule. No, that's probably the hardest that they would have for this type of problem. Yeah. Matthew? Okay, so if you were to actually evaluate, let's say you wanted to do 2b from, just do the antiderivative. What's the antiderivative for this? It's going to be u to the 4th minus over 4 minus 5u, right? And we want to evaluate this from -2, -3 to -2x. So we have -2x to the 4th over 4 minus 5 times -2x, right? And then plug in this, right? Evaluated at also -3. But remember, in the end, I'm going to end up just doing the derivative. Do you see it now? Okay. Let's go to the next page. Fundamental theorem of calculus part 2. So we actually did this already, but they clearly define it here. Okay. So the antiderivative of lowercase f of x is going to be capital F of x, evaluated at the upper bound and lower bound. I know, it's just they clearly define it in this section then. So this stuff will all be reviewed from what we've already done. So we can go through this. One thing you have to make sure is that it's continuous. Okay, so let's go through. So it's going to be 4x plus 2x squared over 2. So that's going to be x squared. See, now we're actually just applying the integral. Okay, we're not doing the derivative of the antiderivative again. Yes, last section. Okay, so when you evaluate an integral, you can either put it in brackets and evaluate at the lower bound or upper bound, or you can get your antiderivative and put a line here. The line and the brackets are just ways to say evaluated from A to B. So remember when we did dy dx and we put a line and then we put, exactly, it's the same approach with integral. So you find you find out what your integral is and then you're evaluated. Okay, now we plug in 6. So it's going to be 4 times 6 plus 6 squared minus, and then 4 times 4 plus 4 squared. What do we get? So the nice thing on this next test, when you have these types of problems, you can always check them on your calculator. I'll need to see some work to support, but you can just do the math 9.
When you, if it were to be -4, would it still be minus?
If it was minus 4, like there would be minus a negative,
Yeah.
then it would be,
Okay.
what did you get for this?
28.
28? Sounds good. 28? All right, next one.
For the next one, did you see the x squared over 2?
Oh, hold on, wait. What's the antiderivative for e to the x? Just e to the x. Evaluated. So, Ben, you're asking me about when I use like the evaluated. When I have more than one term, after I integrate, I always use brackets. It's just, but when I just get one term, I usually just use the line. You can use the brackets every time. It's just when I just get one thing, I just put the line. They mean the same thing. So we get e to the e minus e to the negative 1.
We get 14.7.
Or just leave it like that. Okay, how about the next one?
We have
So it's going to be x to the 4th over
x to the 4th over 4.
plus
4x to the 4th.
x evaluated at negative 1 to 3.
What do you mean 4x to the 4th?
Remember, the rule is that we want to just increase the power and divide by that new power. So we have 3 to the 4th over 4 plus 3 minus negative 1 to the 4th over 4 minus 1.
It's always minus.
It's always minus in between
I think that's what I screwed up on.
that you added them.
Yeah.
So here you get 81 fourths plus 3 minus, and then this is 1/4. The reason I would leave it like this, notice that when you have 81 fourths and you subtract a fourth, that would be 20, right? 80 over 4, which is 20. And then you have 3 minus negative 1, which would be, so you get 24. Does that make sense? Yep. Again, you can always plug this into your calculator, math 9, and then you'll see. How about 3 halves power? What does that become?
5 halves?
Good.
5 halves?
Over 5 halves, evaluated from 0 to 4. Or this would be 2/5, the square root of x to the 5th, evaluated from 0 to 4. Actually, let me put the 5th power on the outside. Well, evaluating it at 0 is easy. Oh, that's supposed to be a 5th. So it's 2/5, and then the square root of 4.
Is that okay if we do it on the calculator instead of
That's fine, as long as you just have enough work to support. What do we get here? Square root of 4 is 2. 2 to the 5th is, so 32 times 2? 64 over 5. Perfect. Are we okay so far? This section isn't so bad because we've done most of the work for it prior to this lesson. Okay, what's the antiderivative for negative sign? Oh, which one is it? Regular cosine. Because the derivative for cosine is negative sine. So it's cosine of theta evaluated from pi over 6 to 5 pi over 6. So cosine of 5 pi over 6 minus cosine of pi over 6. What's cosine of? Good. And minus? Try again. Minus, so just negative root 3. Because you'd have two of them and then the 2's would cancel. Okay, this one, okay, this is a composition of functions, which needs something called U substitution, which we're not learning until chapter 6. So the only way that you can do this at this point would be FOIL. It's not that bad. So what do we have? X squared plus 2x plus 1. So x to the third over 3 plus x squared. What's the matter?
When you do your integral sign, you start from the top of one. You start from the top, right?
We always start with the top. So, like for example, when I plug in 0, I notice that I get 0 for the whole thing. So I just put 0 minus so I don't forget that I have to basically subtract plugging in the negative 1 to our antiderivative. So it's just be careful with your positive and negative signs and check your answer on your calculator. So this is going to be negative 1/3 plus 1 minus 1. So negative 1/3 times the negative becomes positive 1/3. I mean, if you're doing these by hand, it's just a lot of mental math. I mean, the actual calculus involved isn't too bad. Again, you're just working backwards and then plugging in the values. Not annoying. It's time consuming? We don't have class tomorrow. Do we? No. We don't have 8 periods tomorrow. It's Tuesday. Thursday and Friday this week. We only have class 3 days. Just Thursday because Fridays, you don't have school. Yeah, I want to try to finish as much as possible because I hate to say it, I'm going to be missing your class next Tuesday on a review day. But there will be a math teacher here that can help. You'll see.